deal. Okay, so where are we at? So we're in a very fun place right now. We're going to talk about something that is familiar now. So here's a fun sentence. Now that we know, I'll put it in quotations because do you really know? Now that we know about sets, we can take the next step. Now, by the way, I did post a homework, I want to say yesterday morning, and I also posted a quiz. Remember I told you guys are going to have some quizzes and stuff like that? It's very short. It's basically 5 questions. It's not difficult. It won't take you long. Yes. I believe the quiz is due the 30th, so you have a week to do it. And I'm going to post a couple more. Like I said, we want to have one a week. But being that things were, sort of with the state of how everything's been going, we're a little behind on that. But we'll start putting them up there. They won't be difficult. They'll all be on Canvas. They'll, I'm never going to say you have an hour to do it. It'll usually post, and you'll have at least a week to do them, type thing. And they're not going to be long. It's not going to be like watch an hour-long movie and write a paper on it. It might be look at it. Here's an example, or I might ask you to solve a problem that's on the homework or something like that. This particular one, Michelle, is not. So it might be in the future that some of them are, but right now they're not. Does that make sense? Or excuse me, the first one isn't timed. But anyone that is timed, you'll know before you start it how long you have. You might have an hour, you might have a month, a day, who knows, right? Again, these things are worth 5 points. These ain't exactly going to make or break your score. So don't stress about them. They're essentially a way for us to keep you engaged. Fair? So that Mackenzie doesn't babysit too much or read other books instead of math. By the way, before we begin, does anybody have a question about any of the problems on homework? I believe it's 4. Let me look at, I think it's homework 4. Maybe it's homework 3. I don't remember. I get so confused.
It's 4.
Yeah. Does anybody have any questions on it before we begin? If you don't, that's fine. We've done examples. Yeah. I mean, we've done everything that you're asked to do on here. We've already done an example of.
I forget if we went over it or not, but what's an arbitrary set defined as?
Anything. It's just a letter.
Okay.
Yeah. So when I say arbitrary set, I mean, look, so that's a good question actually, because you guys are, I keep forgetting we're just babies. So when I say an arbitrary set, so what I'm going to do is let me switch. Oh no, let me pull something up for you guys right now. So if I go to this. Hold on. No, give me a second. I'm trying to find something. Okay, so is everybody seeing Canvas? You guys at home seeing Canvas?
Yep.
Yep. Okay. So if we click on our web page and we go, by the way, you'll see when I scroll down here, you see quizzes now, homeworks. So if I click on homeworks, practice set 4. What I want to draw your attention to, if you look at, say, problem 1, I said use a Venn diagram to describe the following relationships. So with the context given, I've said nothing about A, B, or C. So what are you supposed to assume? You are to assume they're just sets. Now, they're arbitrary sets. That means I've said nothing about what's in A. I've said nothing about how big it is or how small it is. All I want you to do is I want you to draw a Venn diagram that represents that one set A is contained in another set B, and that set B is also contained in another set C. Do we understand that? So maybe we don't understand that. So maybe we'll do an example like that in a second. Now, the original question was about what is an arbitrary set. Well, look at problem 2. In problem 2, I tell you exactly what the set capital A is and exactly what the set capital B is. They're not arbitrary. A consists of 3 English letters, A, B, and C. What does B consist of? It consists of the first 4 positive integers, 1, 2, 3, and 4. So that is not arbitrary. Now, in problem 3, I am telling you there's some set A. I've said nothing about it. I've only said one thing about it. I said that A is a set and it has n elements. That's all I've said about it. And guess what? Did I say what n was? No, n can be 2. Can it be 6? Now, would it make sense for n to be -5? No. Can a set have -5 elements? That makes no sense, right? So problem 3 is conceptually much more difficult for students because I have assumed nothing about A and B other than how many elements are in each. And I'm asking you to determine, based on that information, sort of how many elements are in the Cartesian product. Now, you might say, I don't even know where to begin. Well, there's a reason I put number 2 before number 3, because number 2 is going to give you a hint on how to answer number 3, if you do number 2 correctly. And you're going to say, I don't know. We did an example like number 2 last week. In fact, I think we did number 2 exactly last week. Did we not? Or maybe something similar. And then if you look at problems 4 and 5 and 6, those are not arbitrary sets. I am telling you specifically what the set is and what its elements are. Now, for problem 7, the reason I'm saying that A, B, and C, I guess I didn't have to say that. I could have just said prove the following, and in context, you would know that A, B, and C were sets. But I'm being very clear here. A, B, and C are sets. I've assumed nothing about them. The only thing I'm asking you to do is to show that these 2 properties hold. Problem 7 will be a challenge for you. We did an example like that on Monday. There's plenty of examples in the book. But you need, and I repeat, you need to understand that you will likely not get them correct right away. And then number 8, I'm asking you to define something. It's in your book. You can Google it if you want. And then I'm asking you to give me an example. And then number 9 is conceptually difficult. And that's part of what you want to gain in this class is experience looking at things like this, because these are notations that are used in advanced courses. So part of what makes this kind of class difficult is you guys, and I don't necessarily mean you guys in general, but students at this level, is many of you are defeated before you even try anything because you're so overwhelmed by the notation. Like, the notation ain't going to hurt you. I mean, I use this joke all the time. Ain't nobody died from looking at this. Some of you might have anxiety attacks, but you ain't going to die from it. I understand it's overwhelming, particularly the first time you encounter these things. But that is what you're here for. We assume I am not a fool. I know that you're going to mess this up. I've taught this before. I know what happens to even the best students. You mess it up. Even the students that think they know it all, F it up. And those who don't have any confidence in yourself, you'll mess it up too. That's how you learn. The best way to learn is to try something and then see how you do it correctly, and then you realize if you messed up, how you messed up. That's the key. The worst thing you could do is just copy down solutions from someone else, because then there's no learning happening. Just my 2 cents. So anyhow, I hope you'll think about this homework. And if you want, I don't know what's the due date. I don't remember. Okay, if you need more time, here, we'll give you more time, and you can ask questions. We'll make it due Monday. Although I would try to get it done sooner than that, because We've already done all this stuff in class. You have examples that you can use. There's tons of examples in the book. But I know some of you will say, I need more time. So you can turn it in Monday. Look, just like that. I am like your saving grace. Well, that's exactly right. Now you won't feel as bad, right? I'm here for you guys. All right, so let's touch on some of this real quick before we move on, because maybe this will be helpful. So let's do some homework hints first. So I'm not going to do all the problems, but I do want to give you guys some sort of example or two to go with each problem. So remember, what is a Venn diagram? And by the way, let me say this. This is important. So unless otherwise stated, and I said this last week, but you guys don't remember these things. That's okay. So these guys represent arbitrary non-empty sets. I don't want to have to write this at every beginning of every problem. So you need, unless I tell you that A has certain elements, you just assume it has elements. We don't know what they are. Yeah, non-empty. That means they're not the empty set. They have at least one element. I mean, when things are empty, it's kind of boring because there's really nothing to say. And as I said to you two classes ago, we have to have this notion of like what an empty drawer is, like a non-empty set, or excuse me, an empty set. We need to have, for certain technicalities, we need to define what it means for a set to have no elements. We call it empty. Just like at home, you could have a drawer that has nothing in it. It's an empty drawer. It's a boring drawer, but nonetheless, it exists. Okay, so if we look at number one, let's draw a Venn diagram. Let's try to do one we haven't done before. So let's do, I don't want to use green, use black. Now remember, when we do a Venn diagram, it's typical, unless we have some other reason, we imagine this big rectangle is all the elements in the whole world. And we call that the universal set. Just like we live in the universe, right? We could say that the Milky Way is a subset of the universe, correct? And then the Earth is a subset of the Milky Way. Does that make sense? For those of you who believe in planets. So let's draw an example that illustrates the following fact. How about we'll do part of the problem for you, and hopefully you can figure out the rest. I want to show that A is a proper subset of B. That means A is completely contained in B. So one way to do that is to take a big circle. I'm just representing it as a circle. I don't have to use a circle, but that's sort of what Venn wanted us to do. And then I'll take a smaller circle and put it inside of it. So here's the idea. So if I call this guy A, and then I call the bigger circle B, the point we're trying to make here is the pink circle is inside the blue. And let's do one more Venn diagram that's a little more familiar to you guys. Before I switch pages, does anybody have a question? This is fun. I don't know what that was. That's it. It's Wednesday. All right. So let's do one that's a little more interesting. Not interesting, but let's take the universal set of all numbers. And let's emphasize something that we do know. Here's one that we do know. We know, for example, that the natural numbers are a subset of the integers, and the integers are a subset of the real numbers. Right? Hopefully you learn this a lot when you're a child. So let's give these guys some color. Well, first, let's use this big blue for R. I don't know why I'm doing that. So that'll be my R, and then inside of my R has to be, whoa, hey now. And then inside of that has to be my, oh my goodness. So this would be my integer, or excuse me, my natural numbers. The green would be my integers. And then the big circle would represent all my real numbers. So we can even color code this. The reals, the naturals, and the integers. And then, of course, these are all proper subsets. So this is an example that illustrates, this is a Venn diagram that illustrates n is less than z less than r. So how do you do problem 1 part A on your friggin' homework? You replace n with A, z with B, and r with C, and draw the same friggin' picture. Voila. Now I just stole all the fun from you.
You download TikTok?
I did not. I thought it was illegal now. I thought TikTok was, I thought Trump got rid of it. What's that? No, I ain't downloading TikTok.
It's so funny.
I believe that it is. I don't have a problem with it.
I found a math shirt I'm gonna get you.
I have lots of math shirts. What's it say on it? What's it say? If it can't be one of those dorky math shirts, what's it say? And no gifts until my birthday, December 14th, which is also the end of the semester.
Yeah, I know. It's gonna get
Remember you brought those sweets from the Oakmont Bakery too. Was that last summer, I think? Was that summer we had you guys?
No, well, you had me last fall.
Yeah, and then I thought I had you in the summer too.
You had me in the summer before.
Yeah. Do you remember last fall? You know what the 1 year anniversary was? What's it say? I can't see.
What part of, and then it's a big board with a bunch of math.
Don't you understand? That's a good one. Remember, do you know what remember last year I said that I took a shower after outside?
Yeah.
It was the 1 year anniversary of that the other day. That's what my Google Photos app showed me. Long story short, guys, not that you care, but I was at a football game last fall and then I had to go to a concert after and I didn't have time to go home and get cleaned up. So I bought a shower on Amazon and I showered outside.
It's like a bag.
It was a bag shower. That's exactly right. What a time to be alive. All right, yeah, we're just chugging along. Any questions about this problem 1 help? So these aren't the same problems you're asked to do, but they're similar, so you can hopefully figure it out. So number 2, let's do a slightly different example. I'll say let A be, let's say S comma T. And then I'll let B be, you guys always have to have similar things. So how about I do B can be 2, 4, 6. So what is A cross B? A cross B by definition is the set of all ordered pairs. So the first ordered pair would be S comma 2. And then I need S comma 4. And then I need S comma 6. So I've ran through all the time when the first guy was S, and now I have to go through the time when the second guy, or when the first guy is T. So that would be T comma 2, T comma 4, and then T comma 6. And then just for full sort of completeness, we can do B cross A. That would be 2 comma S, 4 comma S, 6 comma S, and then 2 comma T, 4 comma T, and then 6 comma T. So I know I went quick there, but again, this is something we covered 2 classes ago. And so being that you guys are all good students, I'm assuming you studied the Cartesian coordinates. Yeah, of course you did. Don't shake your head, Mackenzie. Of course you did. Over the weekend, you're like, this was so damn cool what O'Grady taught us on Wednesday. He taught us this awesome thing that we've already seen before called ordered pairs.
Family was in town. My priorities yet again.
So here's a cool thing to note in both cases. And I'll write it on this page because I want you to make sure you understand it. So note here. So let's sort of that the cardinality of both A cross B is equal to the cardinality of B cross A, and in both cases there's 6 here. So that might be useful for you to understand how number 3 works. Does anybody have a question about this? Let me hide this off so we don't get confused. Dun, 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 dun. Any preguntas on number 1, 2, or 3? So I'm going to skip 3 because that's a little challenging, and I want you to think about it. I don't want to give away any secrets. Now here's one that's similar to problems 4 and 5. So let's assume A equals the following. How about 1, 3, 5, 7? Let's say that this is all the odd numbers. And then let's say the complement of A with respect to, say, N is, well, how do we write that? One way to write it is A take away N. So everything that's in A, excuse me, let me sort of, hold on a second. Let's back up a second. So we talked about this idea of complement last class. Now, And it might be confusing because we talked about some synonyms of it. We talked about this thing called the difference. We used a bunch of different sort of words. So the complement of B with respect to A. So if we say the complement of A with respect to N is in notation, we can write it like this. N minus A or N take away A. And what it is it's everybody in N that's not in A. So if N is all the positive integers and A is all the odd integers, then this would just be the set of all even integers. So let's do another example of this too. We'll choose a different color. And if you have a question, please ask. Does anybody have a question on it? So remember, we could talk about the complement, and if we talk about the complement, that is without context usually with respect to the universal set or whatever set we're sitting in. But when we have context, here I'm saying with respect to another set. So let's do this one. So the complement of, say, B, let's take B to be something like 1, 2, 3. With respect to, let's say, for the sake of an argument, we'll use a different letter. Let's say C equals 1, 3, 5, 7. Well, this is C take away B. So it's everything in C that's not in B. So what's in C that's not in B? And that would just be 5 and 7. So by the way, no one yelled. Spelled that wrong twice. Yeah, I know. Well, the funny thing is, no one, see, this is what actually, well, I guess I should have given you a day. I didn't give you guys at least a day. What I usually do is I wait how long it takes you guys to tell me that it's spelled incorrectly on the homework. Because I made a point to talk about that in class on Monday, right? I said it's not I, it's E, right? Yet on the homework it's spelled incorrectly. You're supposed to tell me this.
Okay, I didn't look at them.
Uh-huh. Well, you should have spoken up.
Yeah, but then you make me feel stupid.
I don't want to make, oh, please don't say that. I don't make you feel stupid. All right. Problems like 6 and 7 and 8 we actually did on Monday. So I hope if you have questions, you can ask. But I think it's time for us to move on. And then obviously the last problem, it might seem very overwhelming, but ponder it. Yes?
7 is like De Morgan's law, right?
7A is one of De Morgan's laws, yeah. So 7A is one of De Morgan's laws for sets, and 7B is a distributive property. So we showed you how to do these things on Monday. We did an example like this. 2 of them, I think, actually. And we also gave you a couple different proofs to show you how you could do this if you wanted to. All right. So we'll let you think about the rest, and if you have questions, you can ask. All right, so now we return to a familiar friend. Functions. You're all familiar with functions. You've been studying them since pre-calculus. You've studied them in calculus. But you're usually in those classes, they just give you a sort of, well, it depends on who teaches it. Often we just give a very simplified sort of colloquial definition of what a function is. We always say it's like you put a number in, it spits a number out. But in general, functions can be much more abstract, and we're going to see that now. So what are functions? These are, as you know, they are everywhere in math and computer science. They just are. And they come in all types of forms. You know, you've been given the standard examples. I could say, okay, at the end of the semester, each one of you is going to be assigned a letter grade. That is a function. To each one of you, I assign a letter grade. Each one of you has a height. I can assign a height to each one of you, right? Each one of you has a birth year. I can assign a birth year to you. That's a function. So we need to give sort of the official definition. And so here we go. So let A and B be non-empty sets. So a function f from A to B is a rule that assigns exactly one element from B to each element of A. We denote this. Now this is new language you've likely never seen before. We put F colon A arrow B. And we write, and this is what's familiar to you guys. We write F parenthesis little a equals little b or lowercase b if B is the unique element of B, capital B, assigned to lowercase a of capital A. So this is a very, very abstract and general definition. We have said nothing about A and B. We didn't say they had to be numbers. We didn't say anything. So you guys are familiar with functions, but you've probably never thought of it from this standpoint. And when we think of it in this standpoint, we also have to be very careful that a function is not just this rule that you used to thinking about from, like, say, algebra or calculus class. A function is, in fact, a few things. It is a rule, which we call f, but it's also a rule on two sets. So it's sort of like a triple. Function is just not one entity. It's actually three things. So we need some terminology. So if we have a function f from A to B, we call A the domain. That's a word that you're very familiar with. We call the set B the codomain of f. So one of the big confusions is you're going to say, isn't B the range? No, not necessarily. It could be, but it's not necessarily the range. The set So let's think about, what do we know about the range? What is the range? That's the word you're familiar with from, like, other math courses. The range is going to be a subset of the codomain, but what is it? Well, it's the set of all B such that f of A equals lowercase b for, or I guess we can't, we can even say the following. And little a is in A. So this is called the range, which is you're familiar with. But some people use the word image. So a very important thing to note is that this range must be a subset, but it could actually be the same thing as the codomain. So a lot of times it's hard at this level for us to appreciate why we need this idea of codomain and range. Why do we distinguish this? Well, that's because a function, depending on what sets it's defined, can mean something different. See, for us, in having our experience merely being the experience from like calculus or pre-calculus math, we're so used to functions just being plug in a number, have a rule that spits out a new number. But that's not necessarily what a function has to be. Right? If you've ever taken elementary CS courses, one of the first functions you learn is the print function. You get the computer to represent something. That is a function. You put something into it, it does something. In computer science, there are lots of functions that just aren't what we think of in terms of mathematics. And so when we're doing things, it's often important, and it's often sometimes not just important, but necessary for us to have a codomain be something, and it's very possible that the range is in fact a subset of that. All right, so another important piece of terminology is we often use the words map and or transformation instead of function. So what I'm saying is there are synonyms out there. Do not be shocked if you read the word map or transformation. We might say F maps A into B or something. So let's look at an example that's unfamiliar to you, most likely. Let A equal the students in CSCI 2017. And let B equal let's say 10, 11, 12, all the way up to say 35. So there is a function that associates each of you with your age. Yeah.
Can I go?
Oh, sure, yeah.
Get someone to take it?
No, no problem. No need to ask. You gotta go, you gotta go. Take care. Yes, all right, sir. So for example, let's how many students are in this class? I want to say, I don't remember how many there are. Let's say, oh, actually I know 1, 2, 3. Say there's 20. So let's call them all. We'll be real cute. S sub 1, S sub 2, all the way up to S sub 20. And we can give these guys names. A sub 1, A sub 2 for age, all the way up to A sub 25. So for example, our function could be f goes from A to B. And each one of you is associated with your age. Does that make sense? That's a function. Now notice that unlike what I could do in, say, calculus class, I'm not able to write down a rule for this. There's no rule that everybody of you follows, right? But it's a relationship. And you can only be one age, right? So it's not like I can assign Abdullah to 2 different numbers. You're one age right now. So that's a function by definition. And it's very likely, notice that I designated my codomain as 10 through 35. I don't think any of you are 10, right? It's probably more like 18 through 22 or 25 or something like that. And so notice that my range is not going to be my whole codomain. Does this make sense? Does anybody have a question about this example? Now let's look at an example that might be a little familiar, but we're going to analyze it a different way. So let's say f from 0, 1 into r given by f of x equals the square root of x, and f from 0, 1 into 0, 1 given by f of x equal the square root of x are 2 different functions. And the only difference is, and this is an important concept, why? Because even though the range is the same, and the domain, the codomain are different. So this is a very important technicality. So maybe I should be more specific here so it helps fuel the fire. Even though their domain and range are the same, the codomains are different. Yes.
How did you determine that the range was same?
So this is a great question. Well, what's the range of both functions? I mean, the rule's the same, so the range is going to be the same, right? Okay, so think about it this way. The square root function, all right? If you look at its graph on 0, 1, what's the highest output it's going to give you? Is 1, right? And on both cases. So the question was, and this is a good question, is how did I determine their ranges are the same? Well, the only difference is for the first f, I said the codomain is all of R. Now that's a completely legit function. And in the second example, I said the codomain is just 0, 1. But in the second example, the codomain happened to be the range. Whereas in the first example, the range is a subset of the codomain, and hence it can't be the same quote-unquote function. The rule is the same, but the function is not. So there is a technicality there, but it's an important one. And that's why I made this example. This kind of stuff would not be any issue in calculus. No one cares about these technicalities. But it turns out it becomes an issue in certain contexts. And so that's why we have to define our functions accordingly. And another thing, a way of saying that is why a function is not just the role f. A function is a role. It's a set A called the domain, and it's a set B called the codomain. So go back to our previous example. Suppose I had some function that I was going to assign people with, say, an age. Well, in general, I don't know, if I don't know what my group of people I'm going to be studying is, maybe I need to pick some realistic thing, maybe between 0 and 105. I don't know. People lived 105. Meanwhile, on one application, I might be dealing with college students where my range would be different. And in another application, I might be dealing with senior citizens, which means my range would likely be different. Do you understand what I mean by that? So a codomain is sort of like maybe all possible outcomes if we're thinking about all crazy scenarios, whereas the range is the specific outputs of a specific scenario. If that makes sense. And again, sometimes it's hard for us to come to terms with this because we haven't seen a reason that it matters yet. And even this example I've given you, you're kind of like, well, you just made this up. Well, sort of, yeah, but sometimes you have to make things up to see where there's holes in the logic. And this is an example where the hole could be in the logic if you don't, sort of have the right definitions. Does anybody have a question? All right, so some more sort of notation / definition. If F maps some set A to some set B, and we take any subset of A, so we'll call it S. And S could also be A. So this actually sort of is a way of we've already said this with the range. So let's not say if, let's say let. We're making a definition. So we call the following set f of s, which is the set of all b such that f of a equals b, and a is an element of s. So we call this the image of s under f. And so the thing to note, if s equals a, f of a equals the range. So this is notation you haven't seen before. Instead of plugging just like a number into this function, we're saying you can create the notation f parenthesis a set, and that means all the output of that set. So let's just real quickly, let's see what this might look like. It's much easier to see this in terms of an example. So let's take here's a cool one. Let's take f, and we're going to go from the natural numbers, or no, we'll go from the integers into R, and let's say f of n is equal to n squared. So this is, the rule is you input a integer and it spits out its square. So let's state some facts we can say about this. So let's note. The image under the integers is just this set. What are you going to get under the integers? If you plug in 0, you get 0. You plug in 1, you get 1. 2, you get 4. Negative 2, you get 4. You plug in 3, you get 9. Plug in 4, you get 16. So this is all the perfect squares. What about f? If I take a subset of that, what if I just ask what is the image of the set negative 1, 1, and 5? Well, this would be what outputs? This would be, what outputs would I get? I'd get 1, and then I would get 25. So this is an example that I would take some time if I were you to try to make sense of. Does anybody have a question about this? What time is it? Now, one of the things that we learn about in an algebra class and in calculus is that if I give you two functions, I can typically add them together in a natural way. But that only makes sense if the codomain consists of real numbers, right? Because if I say I'm going to associate each one of you with your birth city, right? Well, I can't necessarily add your outputs together. What am I going to Pittsburgh plus Cleveland? What the hell does that mean, right? Do you understand what I'm saying? So we just can't. A lot of the natural things that we would normally do when we're studying, say, functions in an algebra class, where we want to talk about adding two functions to get a new one. Well, that doesn't necessarily make sense unless we restrict our codomain. So that's another reason why things like defining domains and codomains are very important. All right, so the next thing we will do, though, is we will classify types of functions. So it turns out that understanding functions that have certain properties becomes very useful in many applications. And we'll talk about that on Monday. So if you guys don't have any questions, I say time is up. Let us go have a great weekend. And we'll give you some practice on this kind of stuff, too, and hopefully you'll ask questions. Does anybody have any questions before we sort of proceed? All right, well then I thank you guys very much. Have a good weekend if I don't see you, and please let me know if you have homework questions. Thanks, guys. Take care. Oh, someone had something. Yeah, Ethan, you do not. It doesn't matter because -1 squared is 1 and 1 squared is 1. So you don't want to write duplicates. That goes back to Jared's question, actually, from last class as well. Why? There's no need to write duplicates. Remember, a set by definition is an unordered list. I mean, there's no reason to have duplicates. All right. Hopefully that makes sense. Does that make sense, Ethan, or did you leave already? I don't even know. Maybe he left. Oh, no. Let's go check. All right. Awesome. All right, guys. Thanks a lot. Take care. Did I save this?